In this video, we're going to take a look at some basic properties of polynomial functions. Some of this may be review, so we're going to go kind of quick here. And if it's not, then you can slow it down and watch it again. All right, so we got polynomials. A polynomial is a function of this form. F of x equals a sub n x to the n, a n minus 1 times x to the n minus 1, blah, blah. We got a whole bunch of expressions here separated by addition signs. These are called terms. Okay. Now, if that's confusing there, you might think of a specific example, something like this. We can say we have f of x equals 5x to the 5th plus 3x to the 4th minus 2x to the 3rd plus 1. Notice I skipped a few terms because here we have an expression where there's missing some terms. We're missing, let's see, a second degree, an x to the second, and x to the first. I left those out. But they're really there, and they're there with coefficients of 0. So f of x to the 5th plus 3x to the 4th minus 2x cubed plus 0x squared plus 0x. That would be the same thing. All right? So these are polynomials. Each thing separated by an addition is a term. So these are all the terms. In our little example here, we had, in this first one here, we have 1, 2, 3, 4 terms written out. These terms are 0 terms, so they don't really count. All right? The largest power is the degree. So that'd be the x to the n. So this is a 5th degree polynomial in this example. A polynomial with powers written in descending order like I did here is called standard form. If you mix these terms up, it's not in standard form anymore. And these numbers a sub n minus 1, so on and so forth, these numbers that multiply each of the x with the powers there, those numbers are called coefficients. Very important there. Coefficients. And the largest term here, the term with the largest power, is called the leading term. Even though it's not always written to the left, it is if it's in standard form, but it's the leading term. And that coefficient is called the leading coefficient. So the 5 here is a leading coefficient. And this expression or this number down here at the end that doesn't have a variable with it is called a constant term. Okay? If we just have a single term, it's called a monomial. So a monomial is something like f of x equals 32x to the 17th. Monomial, one term. All right, so when we have a polynomial function that has degree n, a very important thing here is that a theorem is that we've got n minus 1 local extrema and at most n zeros. So what that means is this. We have our graph here. And, we might be familiar with an x cubed function. So here's a cubic function, x to the 3rd. And we notice that it crosses 3 times. So this is an x third or a 3rd degree. Okay. So n equals 3. Since n equals 3, that means that we can have, according to this theorem, at most n 0. So it's going to cross at most 3 times. Okay. And we can have n minus 1 local extremas. So that means we can have 2 local extremas. Now, you could get another a polynomial like an n or x to the 5th or an x to the 7th that looks like this, but if we know that this is x to the 3rd, we know that we cannot have more than 3 zeros and 2 local extrema. So that's going to be an important theorem as we work with polynomials. All right, so another thing is we want to talk about quickly is end behavior and intercepts. So we've explored some power functions in the previous lesson or in the earlier, And now we want to use our graphing calculator to fill in the end behavior of these functions. So if we take a look, if you got a graphing calculator, you may want to plug these in real quickly and see what you get for the end behavior of each of these. Now, end behavior is what happens as a function goes to the right and it goes to the left. This function that I just graphed here, as it goes to the right, it goes to infinity. As this goes to the left, it goes to negative infinity. Okay, so that's called the end behavior. When we graph this first function, we get a graph that looks something like this. And we notice that we've got a leading coefficient of 2. We've got a degree of 2. As x goes to infinity, that's as we go off to the right, what happens to y? Well, y is getting bigger, so y goes to infinity. As x goes to negative infinity, that means x is going to the left. So as x goes to the left, going to negative infinity, what happens? Well, we notice that y goes to infinity also. The number of x-intercepts we have here is 2. The number of y-intercepts we have is 1. Try the next one, graph it, and see if you can find these degree and coefficient and end behavior of it. So we get a graph that looks like this, which we should expect. It's upside down because of that negative 2, just like with the power functions. And we see we've got a leading coefficient of negative 2, degree of 2, and it's going to negative infinity as we go to the right and to the left. 2 x-intercepts and 1 y-intercept. Let's check the next one. Here we have a cubic function. Try that one out. So for this graph, we get a little interesting one. Looks like this for an x to the third power. And we notice with a leading coefficient of 1, degree of 3, it goes to infinity, going off to the right, negative infinity to the left, 3 x-intercepts and 1 y-intercept. Let's try a couple more here. We got 6th degree now. Let's see what that looks like. And it's a little tricky one to see. You might need to zoom in, but you get this kind of graph here. And we get with our negative leading coefficient, 6th degree, it goes to negative infinity, left and right. And we got 2 x-intercepts and 1 y-intercept. And last one here, we have a 7th degree graph. Let's graph that and see what that looks like. And it's going to look something like this, touching at the origin, dropping down, and coming back through one more time. And we've got a degree of 7 with a positive coefficient here, going down up to infinity to the right, down to negative infinity to the left, 2 x-intercepts, 1 y-intercept. Okay, so let's look at some patterns real quickly. We notice we always have 1 y-intercept, and that has to be true because these are functions. Always going to be 1. Okay, the x-intercepts, well, as we said before in the previous theorem, these can be up to n minus 1. So a second degree can have up to, sorry, I said that wrong, up to n x-intercepts. So this can have 2 x-intercepts, this can have 2, this can have 2. This could have 6, but it doesn't have to. This one could have 7 x-intercepts, but it only has 2. So that's a maximum. Now, notice the end behavior here. Okay, when we have an even function or an even even degree, they're either both going to go up or both going to go down. Same thing if we have x to the 6th, or if we had x to the 16th, that would be the same. Okay, as far as end behavior, they're either both going to go up or both go down. When we have an odd, degree like x cubed, well, it's going to go down to one side and up to the other. If it's positive coefficient with an odd degree, then it's going to go down to the left, up to the right, just like this positive x is 7th. Now, we should expect that if we have a negative, like a negative x to the 7th, well, that graph's going to look something like this, and it's going to flip. Okay, it's going to do something like this. So the negative will make the end behavior switch. So negative would take the left end behavior to infinity and the right end behavior to negative infinity. So a couple quick examples to wrap it up. Here the question is, what is the least possible degree of the polynomial function in the graph shown below? Well, if we look at this graph here, this first graph, we see 1, 2, 3, 4 extremas Okay, 4 extremas. And, well, we see that we have 1, 2, 3 x-intercepts, but if we were to slide this thing down and make it cross here, we could get more x-intercepts. Can you imagine that? If we were to slide the red curve down, that would give us more. So let's just use the fact that we have 4 extremas, and that tells us that we know we could have a 5th degree. Notice it's also going down to the left, up to the right. So this is 5th degree, because it's the number of extremas plus 1. It could be a 7th degree or some other odd degree that's bigger than 5, but we know it has to be at least 5. Here we have 1, 2, 3 extremas. Okay, 3 extremas there. And so we know that this would have to be at least a 4th degree, because it's number of extremas plus 1. Okay? All right. Also notice it's going both down, so this would be like a negative x to the 4th. Okay, one more here. We got, how about the vertical and the horizontal intercepts? Well, we've got a function here, f of x equals 4 times x plus 3 times x minus 4 times x plus 1, and we want to find out where this crosses the x and the y axis. Well, when it crosses the x-axis, we know we have a y value of 0. So when y is 0, this equation becomes 0 equals 4 times x plus 3 times x minus 4 times x plus 1. And we should remember the zero product rule, which says when you have a bunch of things multiplied together and they all multiply to 0, one of these things has to be 0. So we ask ourselves, what makes x plus 3 equal to 0? And obviously, that is 0. I'm sorry, that's negative 3. And then we got to ask ourselves, what makes x minus 4 equal to 0? And that's obviously 4. Add 4 to both sides. And then what makes x plus 1 equal to 0? Subtract 1, and that's negative 1. So there's our x-intercepts. Now we want to figure out our y-intercept, and our y-intercept here happens when x is 0. So when x is 0, we have our y-intercept, and so what we need to do is take our function and find f of 0, which is 4 times 0 plus 3 times 0 minus 4 times 0 plus 1, and that gives us 4 times 3 times negative 4 times 1. And that should give us 3 times 16, or negative 16, which is 48 negative. So we get negative 48, and that is our y-intercept. Okay? So our y-intercept is at negative 48, and our x-intercept are these 3 different times. It crosses 3 times. Notice, by the way, if you multiplied this whole thing out, if you did some foiling, distributed, and distributed, you would end up with x to the 3rd. This would be a 3rd degree polynomial, and because it's a 3rd degree polynomial, it can cross up to 3 times, and it does cross 3 times. So there you have it. That's how we find polynomials and work with polynomials, find their end behavior and some intercepts, and we got all kinds of good vocabulary there. So polynomials, hugely important, very important part of algebra and pre-calculus. So take it from there.